Welcome to another lecture on engineering mechanics. Today we will discuss two topics. The first is moment of a force, and then we will learn about couple. Let us start the lecture. Let us first see turning effect of forces. So far we have dealt with concurrent coplanar force systems where the turning effect of a force does not exist. Turning effect of a force becomes very important when we deal with non-concurrent force systems. Let us see one example of turning effect of force. It is common experience that when we push or pull a door by holding at the handle, the door opens by rotating about the hinges which connect the shutter to the door frame. So let us understand over here. So we are shown one door and shutter is also shown for that door, and these are the walls, and this is the frame of the door, and these are the hinges which connects the shutter to the frame of the door, and then we have a handle of the door. So when we apply force on the handle of the door, when we push or pull a door by holding at the handle, the door opens by rotating about the hinges, which connect the shutter to the door frame. The shutter is prevented from moving forward as a whole because of its connection with the frame through the hinges. You might have also noticed that the handle is placed as far from the hinges as possible. You can easily find out for yourself that if you have to open a door, it requires a large force when applied near the hinges than when the force is applied away from the hinges. So, the turning effect of a force is measured by a quantity known as the moment. So what is moment? Moment m of a force F about an axis is defined as the product of the force F and the perpendicular distance d from the axis of rotation to the line of action of the force. So it will be equal to m equal to the magnitude of the force multiplied by the perpendicular distance of the force from the axis of rotation. Now let us understand this through this example. So over here we have shown one axis, that is z axis, about which this door rotates on the application of force at the handle of the door. So let us apply a force F. It is a pull on the handle of the door, and let us say the distance of the point of application of the force, or we can say the line of action of the force from the axis of rotation is, let us say, d units, and this is the perpendicular distance between axis of rotation and the line of action of the force. So if we have to find out the turning effect produced by this particular force on the door shutter, then that will be equal to the product of the magnitude of the force applied into the perpendicular distance, and this distance is between axis of rotation and line of action of the force. Now let us understand few more terms over here. When we will draw the perpendicular distance, it will intersect the axis of rotation at some point. Let us call that point as O, and we call that point as moment center, means that point about which we want to find out the turning effect of the force or the moment of the force. So we call that point as moment center. Next is moment arm. Moment arm is the perpendicular distance between the axis of rotation and the line of action of the force. Next is axis of rotation or moment axis. So it is the axis about which we apply the moment. Now we'll discuss few important points over here. So listen very carefully. The first point is the moment arm is at right angles to both the line of action of the force and the moment axis. This we have already discussed. So the moment arm is perpendicular to the axis of rotation, see over here, and it is also perpendicular to the line of action of the force. The force lies in a plane perpendicular to the moment axis. Now let us understand this point. This is the plane of the force. In this plane, this particular force is acting. But if we see the plane of axis of rotation shown over here, then you can see both the planes are perpendicular to each other. So that is why it is written the force lies in a plane perpendicular to the plane of moment axis, or we can say to the moment axis. Next point is the moment of a force is dependent upon the magnitude of the force as well as the moment arm. Of course, when we will calculate the turning effect or the moment of this particular force, we know that is equal to the product of the magnitude of the force and the perpendicular distance. So, the moment is dependent upon the magnitude of the force as well as the moment arm. Now we will discuss the nature of movement. So over here we are taking one example. We are taking the example of a revolving door. So this is a revolving door and this figure is the top view of the situation when a person wants to go to the other side of the door. Now suppose the person wants to go to the other side of the door from this particular side, then he will apply force at this particular point on the door. Now let us see what will happen then. So if we will apply a force at this particular end of the revolving door, then this door will rotates in anti-clockwise direction. So if we have to find the moment of this particular force about this particular center, then that will be equal to the product of magnitude of the force and the perpendicular distance between the line of action of the force and the axis of rotation. Now whatever value we will get, we have to tell about the nature of that value or nature of that moment generated by this force. As we have seen, because of the application of this force, this door rotates in anti-clockwise direction. So it generates anti-clockwise movement. So we consider anti-clockwise movements positive. You will find that some books consider anti-clockwise movements negative. So it is purely assumption. Don't get confused. Some books use anti-clockwise movements negative and some books use anti-clockwise movement positive. This is only done to talk about the nature of the movement. So in our textbook, positive sign is used for anti-clockwise movements. So we'll stick to this particular assumption only. Now let us see what will happen if this person wants to go other side of the door by applying a force at this end of the revolving door. If person applies a force of magnitude F at this end of the revolving door, then door will rotate in clockwise direction. So we can say this particular force has generated a turning effect which is in clockwise direction. Or we can say this force has generated a clockwise movement. We consider clockwise movements negative. So this we should keep in our mind. Whenever we have to solve some problems, we have to see the nature of movements as well. If the movement is anti-clockwise movement, then we will consider the value of that movement as a positive value. But if the nature of the movement is clockwise, then we have to consider the magnitude of those movements as negative in the problem. Movement is also a vector quantity like force. In order to specify movement, it is not enough to state the magnitude of the movement. We have also to mention the nature of the movement and the axis about which movement is taken. So this we have already discussed, that whenever we have to talk about any movement, we have to give its magnitude, and we have to also talk about the nature of the movement, and we should also talk about the axis about which we have taken the movement. Next we will learn about principle of moments, or it is also known as Varigonance Theorem. This is a very important theorem. We use this theorem in solving problems related to moments. So let us first see the definition of this theorem. It states that the moment of the resultant of two concurrent forces about any point in their plane is equal to the algebraic sum of the moments of these forces about the same point. Now let us understand this through an example. Over here, we are considering two forces. The magnitude of one force is F2 and the magnitude of other force is F1. These two forces are coplanar and these two forces are concurrent also. So they are forming a system of coplanar concurrent forces. Let us say this is their plane. Now in this plane, let us consider one point and let us name that as O. And this is the moment center. Means about this point, we will calculate the turning effect of these two forces separately. Or we can say the moments generated by these two forces about this particular point. So let us first see the perpendicular distance between the moment center and the force F1. So for that what we have done, from moment center we have drawn one line which is parallel to this vector F1. Then the perpendicular distance between these two lines will be the moment arm for the calculation of the moment because of force F1 at this moment center O. Next let us see the distance of F2 from the moment center, or let us see the moment arm for F2 in order to find the moment generated by F2 about this point O. So for that what we have done, from moment center we have drawn one line parallel to the vector, and the perpendicular distance between those two parallel lines will be called as moment arm for the second force. Now let us calculate the moment of force F1 about point O. So what will be that moment? That will be equal to product of magnitude of force F1 and the moment arm, that is D1. So it is M1 equal to F1 into D1. Now let us calculate moment of force F2 about same point O, moment center. So what will be that moment? that will be equal to product of the magnitude of force F2 into moment arm. So see over here, M2 is equal to F2 into D2. Now we have found the moments generated by these two forces about a moment center which is in their plane. Now let us see what is the meaning of this theorem. Suppose R is the resultant of these two forces and we want to find out the moment of the resultant force about the same moment center. Then we can make use of this theorem. This theorem states that the moment because of the resultant of these two forces about the same moment center will be equal to the sum of the moments of the individual forces about the same moment center. So we can write moment of a resultant about point O will be equal to M equal to M1 plus M2. So these are the individual moments of these two forces about the same point in the plane. So this particular theorem is very useful in solving some problems on moments. So I hope this theorem is clear to you. Now we'll take one example on moments. So let us read the problem. A 100-pound vertical force is applied to the end of a lever which is attached to a shaft at O. Determine A part, the moment of the 100-pound force about O. So we will solve all these parts one by one. So let us first solve A part only. And before that, let us understand the problem. So we are given one lever in the problem. This diagram is given to us. And at point O, one shaft is attached. So about that shaft, this lever can rotate. Fine. Now he is saying that a 100-pound force, which is a vertical force, it is acting in downward direction, is applied at A, and for the position shown the angle of lever with the horizontal is 60 degrees and the length of this lever OA is 24 inches. This is given to us. Now what we have to find in A part? In A part we have to find the moment of this particular force about point O for this particular position shown. Okay, so we have learned in the previous slides that if we have to find the moment of any force about any moment center, then we have to multiply its magnitude by the perpendicular distance it has from the moment center. Means we have to first find the perpendicular distance, we call that as moment arm. Then we have to multiply that with the magnitude of the force in order to find its moment about the moment center. It means first step is we should find the moment arm. So how to find the moment arm? Let me tell you a very simple procedure for this. I have seen that most of the students get confused while finding moment arm. So they get wrong answers. So let me tell you a very simple procedure over here. In order to find moment arm, what we will do, we will first sketch the line of action of the force for which we want to find the moment. So let us sketch the line of action of this particular force. So this is the line of action of this force. We have extended this vector. After that, what we will do, from the moment center, we will drop a perpendicular onto that line of action like this. So see, it is a perpendicular. So We will name that intersection as B. So for force, the moment center is OB. So whenever you have to find moment center, first of all you should draw the line of action of that force. Then from the moment center, drop a perpendicular onto that line of action. So that particular length will be called as moment arm. So in this case, moment arm is OB. Now, first of all, we have to find the value of OB. So how to find? Now we have to apply mathematics over here, or we can say trigonometry over here. We have a triangle now, OAB, and it is a right angle triangle. So if we want to find OB, then we can make use of cos theta. We can say cos 60 degrees is equal to base upon hypotenuse. So base OB will be equal to hypotenuse multiplied by cos 60. So look over here. We have found OB. It is a perpendicular distance or moment arm. So this is equal to hypotenuse multiplied by cos 60. So we got the answer as 12 inches. Now we have the moment arm. So when we will multiply this moment arm with the magnitude of the force, then we will find the moment of that force about the moment center. So let us calculate that. So you can see moment about O will be equal to magnitude of the force into the moment arm. So we got our first answer 1200 pound inches. Now very important point to understand about the units of moment. Now you see moment is the product of force and the distance. So we have to write the unit of force plus the unit of distance. So that is why its unit will be pound inches. Now another point to understand, as we discussed in the previous slides, that along with the magnitude of the force, we have to talk about its nature as well. Fine. Now look over here. We have to find its nature now. Means we have to see whether it is a clockwise movement or it is an anti-clockwise movement. Now how to find? Focus on this particular vector. Over here is the moment center. Now in order to find its nature, we have to find the closest path which this vector has to travel in order to, let us say, reach to this moment center. So closest path will be this only. Fine. If we draw like this, that it will go other way around. So that is the longest path. Fine. So that will not consider. Closest path will be, it will try to move towards the moment center. So in that process, the movement it will generate will be clockwise movement. You see, it will try to move towards the movement center. So it will generate clockwise movements. So this way you can judge whether the movement is clockwise or anti-clockwise. But if you consider its longest path, let us say it will move this way around. So that cannot happen. So that will be an anti-clockwise movement. So we will choose the shortest path. So shortest path means it will try to move this lever in this direction only. It will not move the lever in this direction. Fine. So it will go this way around because it is in downward direction and movement center is here. So this is the shortest path. Fine. So remember this, how to find the nature of the movement. Think about the shortest path. So this particular nature is clockwise. So we will say the movement this particular force will generate will be clockwise movement. So now we have two options. Either you can put a negative sign in front of it or you can write that it is a clockwise movement. You have both the choices. I hope the first part is clear to you. Now let us discuss the second part. Second part is find the horizontal force applied at A which creates same moment about O. So in the second part, he is saying that apply a horizontal force at A and then find what should be the magnitude of force A if it generates same moment about O which we have calculated earlier. Fine. So let us draw a horizontal force at A. Now we have to find its magnitude. Let us say it is F. And we have to find its magnitude, and it is provided that this force is also generating same moment about O. So in order to find its magnitude, again we will think about the formula of moments. So formula of moments is moment is equal to force into momentum. Now moment for the B part is given to us. He is saying same moment we have already calculated. So in the formula M is equal to FD, we know M for B part and we have to find F. And if we can find D, that is a moment arm for this particular force, then from the formula M is equal to FD, we can easily find F. So it means now our first step is we have to find moment arm, that is D, for this particular force about moment center O. So what we will do for that? We will first sketch the line of action of this force. So let us sketch its line of action. So this is the line of action of the force. So in order to find the momentum, what we will do? From the moment center, we will drop a perpendicular onto this line of action of the force. So this is the moment arm for this force, and this moment arm is over here actually, AB. So AB and this length both are same. So in order to find moment arm for F, we can find this length AB from triangle OAB. So what will be that length? Now we will apply the formula of sine theta. We will say perpendicular AB upon hypotenuse 24 inches is equal to sine 60. So we can find AB equal to 24 multiplied by sine 60. Okay, let us see the calculations now. So in B part over here we have written M equal to F into moment arm. Moment arm for this particular force will be AB. Now as he has written, which creates same moment about O. So we have taken the previous moment here. Now we have to find F and we have to find AB first. So we have already found AB. AB will be equal to 24 inches into sine 60. So see over here, AB 24 into sine 60. So after this we will put the value of AB over here and we can get the value of F. So that will be equal to 57.74 pounds. Now let us move to the next part of this problem. What is the next part? Next part is the smallest force applied at A which creates the same moment about O. Means we have to find the smallest force applied at A again which creates the same moment about O. Now very important point over here we have to understand. He is talking about smallest force and we know the formula of moment is M is equal to F into D. Now smallest force and he want to keep same moment, that is 1200 pounds. So this left hand side he wants to keep same, but he want this to be minimum. It means we need to increase this. Fine. If we want to find a minimum amount of force required to produce same moment, that is 1200, then of course this part should be maximum, that is moment arm should be maximum. Now over here we have to understand one thing, that how and in which direction we should apply that minimum force so that the moment arm should be maximum. Bache, over here we are given one lever and in order to use maximum moment arm we have to use full length of the lever, that is 24 inches. So if we have to use 24 inches complete length of the lever, that is maximum length, as maximum moment arm, then the minimum force should act at 90 degrees to the lever, because in the previous slides we have learned that moment arm is always at 90 degrees to the line of action of the force and 90 degrees to the axis of rotation. Fine. So over here we have to apply force F. So this will be the minimum amount of force required to produce same moment, that is 1200. Fine. So you see, we kept this at 90 degrees to the moment arm. Fine. So that condition is satisfied. And only then we can use the complete length of the lever. Fine. So now let us find its solution. So same moment 1200 equal to F into 24. That is the complete length of the lever, that is maximum moment arm. So from here we will get minimum force required to produce same moment. Now let us see the D part. Determine how far from the shaft a 240-pound vertical force must act to create the same moment about O. Now he is asking us that how far from the moment center we should apply a vertical force on the lever so that moment should remain same. It means we have to locate a point on the lever from O, and when we apply a vertical force of 240 pound on that point, still movement should remain same. Fine. So let us consider an arbitrary point first. Let us consider a point on the lever, and right now we don't know this distance. This we have to answer in D part. We have to answer how much will be OE. So we have just taken a point on the lever. Now let us represent a vertical force on that lever. So it will act in downward direction and its magnitude is mentioned to us as 240 pounds. Now again he is saying same moment. So if you consider that formula of M is equal to FD, M is already given to us 1200, same moment. But we are given this time this force as well, 240. Fine. But moment arm is not given to us. So from the formula M is equal to F into D, we can find moment arm first. So let us find the moment arm. So what will be the moment arm for this particular force? Let us see that also. So for that what we need to do? We need to draw its line of action first. So let us draw its line of action. So we have drawn its line of action over here. Now from the moment center, drop a perpendicular onto that line of action. So let us say this point is D. So moment arm for 240-pound force is OD. Fine. So when we will apply the formula that M is equal to F into D, from that formula we can get OD. So let us first find OD. So OD is 5 inches. So we have found this distance 5 inches. Is this our answer for D part? No, this is not the answer, bache. Look over here, what we have to answer. We have to answer how far from the shaft. Where is shaft? Shaft is at O. So how from the shaft on the lever we can apply the force. So we have to answer this distance, OE. Fine. So now how you can find OE? Very easy. We will consider this triangle OED. We have found OD and we have to find OE. So we will say cos theta. Cos 60 is equal to base OD upon hypotenuse OE. Look over here. So OD from cos 60 will be equal to OE into cos 60. So we'll get OE as OD divided by cos 60. So that will be equal to 10 inches. So I hope this particular numerical is clear to you. Thank you very much.